All right, welcome everybody. We're going to get started here. First of all, I'd like to thank you all for attending. I'm very excited to be doing the first online live training of 2015. So we are testing out the Google Live broadcast for the first time and a screen share slideshow whiteboard, online whiteboard as well. So we are doing testing of two new systems here, so bear with me if we have any glitches. I don't think we will. So this online training is for my online HVAC students, and it culminates modules 1, 2, and 3 because the refrigeration cycle is covered in depth in module 1, 2, and 3, and this is just one of small live trainings that we do just to reinforce what they're learning online as well. And I've invited all of you to attend because this is our beta test. So I wanted to have as many folks as possible just to see how it handled large numbers of people. So welcome. If I can help you in any way, just let me know. So let's get started. Okay, so tonight we're going to talk about a fixed orifice system. And we'll go over the refrigeration cycle of a fixed orifice system and just review the refrigeration cycle. We're also going to review some key terms that we're going to be using as well. Then we'll go through the refrigeration cycle with an undercharged system and see how that affects superheat and subcooling and why. And then we'll do the same thing with the overcharge. We're going to be about 30 to 45 minutes. I will keep it moving along. I know it's getting late for a lot of folks. And then we'll have a question and answer period. And Andy, I saw your question there. I'll talk with you about the vintage soda machines here at the end. And after we get done and see if this pertains, I might be able to help you offline here. All right. So let's get started. Okay. So quick review. We need to remember that heat is are actually molecules in motion. The faster these molecules vibrate and move around, the more heat we have. And I like to tell my students to get cold and cool out of their vocabulary and talk about more heat and less heat. And remember that, you know, if we look at these temperatures right here, they are cold as far as we're concerned. They at minus 200 and minus 350 degrees Fahrenheit, that's cold to us, but it still contains heat and it still has molecules in motion. So if we put these two blocks next to each other, the minus 200 degree Fahrenheit block of material and matter has more molecules in motion than the minus 350 degree Fahrenheit block, and that heat will flow from the substance that has more heat to the substance that has less heat. All right, so heat flow goes from a substance with more heat to a substance with less heat. Remember, heat are molecules in motion. All right, so we also talk about gas laws in modules 1 and 2, and this is an example of a piston, and in this it has an air cylinder at atmospheric pressure with air in it, but the principles are the same. So the air inside of this piston has molecules. Those molecules are in motion and are bouncing lazily around in here. It has low pressure and the temperature is fairly low. But as we move this piston upwards, those molecules have less space to bounce around and they start to vibrate faster and faster in here. And what that does is increases the pressure, and because they're moving faster, those molecules in motion increases the heat. So there's a direct relationship between pressure and temperature. So as the pressure increases in a system, in our air conditioning system, so does the temperature. And then conversely, if we decrease the pressure in this vessel, then the temperature goes down and vice versa. Okay, sensible heat. Key term here. So sensible heat is if heat is added or removed from a substance and the temperature changes, that is what's called sensible heat. So and that you can measure the change in temperature. So if you put an iron rod over a flame and you put a thermometer on that iron rod and that thermometer starts to increase in temperature, we are now absorbing sensible heat. And remember, heat's molecules in motion. Latent heat, that is when heat is added or removed and it changes the state of the substance. And in our case, that's the refrigerant. So when there's a change of state, all of that heat energy that is added or removed is absorbed and used to change the state of the refrigerant. And if you put a thermometer in there while you're adding heat and it's changing state, the temperature doesn't rise. And we'll go through an example of using water here with sensible and latent heat before we get on to the refrigeration cycle. Remember, changing state in our field is from liquid to vapor. And when refrigerant changes from liquid to vapor, it requires a tremendous amount of heat energy to make that change. And that's why refrigeration works. And then the other change of state in our refrigeration cycle is vapor to liquid. And that releases all of the heat, all this heat that's required to change the state from liquid to vapor. It's released when the refrigerant condenses back down from vapor to liquid. All right, so change of state is where the refrigeration process happens. Okay, let's take a look at this diagram. This is a diagram out of our textbook, and it starts down here at with minus 17-degree ice. We're not going to talk about the ice raising temperature and melting. We're going to talk about 32-degree water, and we're going to start right here at this part of the graph. So we take 32-degree water, and this is our BTU content here. So as we begin to add heat, the temperature begins to rise of our water from 32 to 50 to 60 to 100. This is sensible heat. So it raises the temperature up to 212 degrees, which is the boiling point of water. And as you can see in this diagram, it only takes 180 BTU of sensible heat to raise the temperature of 32-degree water to 212 degrees. And this is 1 pound of water, by the way, not 5 gallons of water. All right, so that is our sensible heat. So again, as the heat is added and the temperature rises, and you can measure it with a thermometer up to 212 degrees, this is our sensible heat range. As soon as we hit 212 degrees, the water starts to boil. That's our change of state that's happening with the water. Now remember, the change of state, as we add heat, the temperature can't be measured and doesn't rise. So we plateau up here at 212 degrees, and this water continues to boil, and it changes state and changes state and changes state until it is completely converted into vapor. So when it's changing state, it's going from liquid to vapor. And as you can see, it takes almost 100 times more, a little bit less than 100 times more heat energy to boil that and change the state of that water than it does to raise the temperature. And that's why we have we're able to remove a lot of heat out of the space that we need to when we're running our refrigeration system. Okay, so we get back up here. We've changed state, and now all of the water has changed state from liquid to vapor. We're at this point right here, and we are at 100% vapor. And if we continue to add heat, then the temperature again starts to rise, because that vapor, it can no longer change state. There's no more liquid to boil off. So this is again back in the sensible heat range. And when we do the refrigeration cycle, we're going to look at a little bit of sensible heat on this end of the scale. Then we're going to take a look at all of this latent heat that happens on this scale. And then we're going to take a look at just a little bit of sensible heat on the other end. And that's why it's very important to understand sensible and latent heat and changing of state. All right, I'm going to take a quick break here, see if there's any questions. I cannot see the question box while I'm doing the whiteboard, so I don't want to leave anybody hanging so far. So let's see if we have any questions, and then we'll pop back. Okay. So far, so good. Let's move on. Okay, so we're going to talk about a residential air conditioning system that has a fixed metering device or a piston. And again, remember, some of you are air conditioning technicians. This is old hat to you, but I do have people that in my class that have never seen a piston before. So we'll just do a little quick review of that. So this is the piston, side view and front view. And basically it's just a brass device that has some nylon fittings on or bushings on the end here and a small orifice for the refrigeration to flow through. Now that orifice fits into this part of the evaporator coil, and I'll give you a closer look. So this is a good example here. This part right here is this what you're looking at right here, right? So the fixed orifice is in this. Let's change some colors here. Fixed orifice is right inside of here. This just happens to be an air conditioning system that had leaks for 3 years, and the company that came out continued to add refrigerant, couldn't figure out why. And can you figure it out, you guys that know what air conditioning, that work in air conditioning? Well, they put the nylon O-ring on the wrong side of, even though how they got 2 of them on here, on the wrong side of the liquid line where it fastens in. These should be up here. So what I did of how it's where it's supposed to be, and again, there's one, this white one right here should have been over on this side, and then there was a bigger black one over here that someone put over the top to try and keep it from leaking. So you always find that kind of stuff that's just not covered in textbooks when you're out there in the field. Okay, let's take a look at our refrigeration cycle, and let me just explain what we're looking at here. This is the wall to the house. This is the inside of the house where the air handler is. Our air handler has a fan to move the air over the evaporator coil, which is right there. All right, got that? And the same thing, now let's stay on this. The room air the room air that we have flowing over the coil is 75 degrees Fahrenheit and at 50% relative humidity. So on the other side of the wall is our condensing unit, the outdoor unit. We have our outdoor fan and compressor, and we have outside ambient air temperature of 95 degrees Fahrenheit. Let me clean up the board here. Okay, now that piston that we looked at, or the fixed metering device, is represented by this part of the diagram. It shows that that's a restriction in the line. When you look at real air conditioning systems, the refrigeration lines are different sizes, but for the purpose of demonstration and illustration, they are the same size. So we have this little bottleneck right here that represents our fixed metering device. All right, so we're going to start out here at the compressor, and we're going to go through a refrigeration cycle of a system that is properly charged, and we'll talk about what happens with the refrigerant and see what happens with superheat, subcooling, and the sensible and latent heat and so forth. All right, so let's start out here. Leaving the compressor, we have high pressure, high temperature vapor, and it's superheated. It has superheat in it. That's on the end of that chart there, and it is pretty hot, and it leaves the compressor and enters the condensing unit outside. And at this point, it's 100% vapor, and it's de-superheating, so it's shedding that heat. See, it's 200 degrees of refrigerant vapor. The outdoor air is 95 degrees. So we know that those molecules in motion are going to travel from a substance that has more heat energy, which is the refrigerant, to the outside air, which has less heat energy at 95 degrees Fahrenheit. So we're de-superheating at this part of the refrigeration cycle. So the temperature is going from 200 degrees and it's going down to a 95 or 195 to 190. And at a certain point, as it's designed to in the condensing unit, it will now have shed all of the superheat, all of that sensible heat, and it will start to change state from vapor to liquid at this point. When it starts to change state from vapor to liquid, the temperature stops dropping and it remains, and in this example, at 125 degrees Fahrenheit. And so at this point, the refrigerant is at 125 degrees Fahrenheit, and now it is starting to change state from vapor to liquid, or we're condensing back down. So as we move through the condensing coil and this fan is blowing the 95-degree air over the top of that coil, more and more heat is removed from this refrigerant, and it will continue to change state from vapor to liquid, vapor to liquid. All of that heat is required to change it to vapor is being released outside. So at the point halfway through our condenser, it's now 50-50, 50% vapor, 50% liquid, and it continues on through the system. No matter what point while it's changing state that you put the thermometer here, here, or here, it's all going to be 125 degrees, because remember, when it's changing state, it doesn't change the temperature, but it is getting rid of the heat. All right, so we're again changing state. Now we're starting to get to the point where it's 75% liquid, 25% vapor all the way through. And at a certain point, when there's a properly charged system, the refrigerant is now 100% liquid. And when it's 100% liquid, it is still at 125 degrees. It is still has more heat energy than the outside air, and it will continue to shed heat. However, the heat that is shedding is not that much, and it is sensible heat. So it's going to start to drop the temperature of the refrigerant, that liquid refrigerant, as it starts to travel back in towards the indoor unit. And as it gets up to the metering device, it is, in this example, down to 105 degrees Fahrenheit. And it's 100% liquid. We have a solid column of liquid hitting the metering device. That's what we want to have. The reason that you want to have a solid column of liquid and subcooling, first of all, the reason we want to have subcooling in our refrigeration system is every bend that you have in the liquid line, any ding from the lawnmower, any long length of pipe or a poorly brazed joint begins to drop that pressure, and which drops the temperature. And if we don't have enough sensible heat here in this line, it's going to start to flash over into gas before we hit this metering device up here. So let's take a look. We have our gauges on the system, and right here, you're sitting out at the condenser with your gauges. You're looking at 278 psi-G on your gauge. So you're going to look at your gauge or your pressure temperature chart, and you're going to look over here at R22. This is that column right there. This is from our textbook. We're going to look at 278 psi, is equivalent to 125 degrees, just like in our diagram over here. So it is 125 degrees. Now remember, when you have your gauge on the system, your high side gauge on the system, and you're looking at this pressure and you're converting it over to the temperature just like we did, you'll notice that here it is right there, 125. You'll notice that that pressure converts to 125 degrees Fahrenheit, yet you have your thermometer right here, right where your gauge is connected to the liquid line, and it's reading 105 degrees. And that gets confusing for some new technicians. So what you have to think about is when you hook your gauge up to the liquid line or the high side, you need to picture in your mind that you are measuring the temperature at the exact center of the condensing coil. All right, you're looking at what's happening here in the center of the condensing coil. You're not looking at what's happening here where your gauge is connected. All right, so what you're doing is your gauge tells you the saturation temperature and pressure of the refrigerant in the middle of the condensing coil, and then your thermometer tells you what the temperature actually is after it's been subcooled. All right, and the way that we get our subcooling in this is we take the 125 degrees Fahrenheit that we read on our gauge, and then we take our 105 degree Fahrenheit that we are reading from our thermometer at the liquid line, and we subtract the physical temperature of the refrigerant line from the saturation temperature. And in this example, we have 20 degrees of subcooling on the system. And that is a properly charged system. In this example, manufacturers are different, and this ensures we have a solid column of liquid hitting the metering device, and this is operating properly and everything is good to go. All right. So we have our solid column of subcooled liquid hits our metering device. Now remember, when we looked earlier, when you reduce the pressure of refrigerant or any kind of gas, it reduces the temperature as well. And that's what this metering device does. It is a restriction. And basically, it's like putting your thumb over the end of a hose and it starts to spray that refrigerant into the evaporator coil. And right at the metering device, as it exits the metering device, it is 75% liquid and 25% vapor. That flash gas is what that's called. That 25% vapor has actually no cooling capacity at all. It is part of the refrigeration process, but it has no cooling. So the manufacturers have to design the coils so that they're large enough to compensate for that 25% vapor, and that the rest of the liquid that makes it on through to the evaporator coil is sufficient to cool the house. So you don't have to worry about that, but you do need to know that 25% of the refrigerant flashes over as soon as we hit the metering device. All right, so we start out here at the exiting the metering device, and it's 75% liquid, 25% vapor, and the pressure has dropped and the temperature has dropped. And let's take a look at where we're at here with the pressure in, or the temperature in the evaporator coil. So here's our gauge over here. So we have, again, we've dropped pressure and we have a temperature drop as well. So here is our suction line gauge. And just like our condenser, when you hook up your suction line gauge outside, you are really looking at what's happening in the middle of this evaporator coil. All right, you're not looking at what's happening right here. You're looking at what's happening right there. So what is 69 psig temperature-wise? What's the equivalent temperature for that? Your gauge will tell you, but let's look at our ET chart here. And let's find 69. There's 68.5 degrees in the green column. And we come over here, and that tells us that the refrigerant in the middle of that evaporator coil is at 40 degrees. All right, so let's write that up here so we don't forget. 40 degrees in the evaporator coil, right in the center of the evaporator coil. It's throughout the evaporator coil, but I still want you to picture it right in the middle of it. Okay, so metering device. We have our flash gas, 75% liquid, and it is 40 degrees out, 40 degrees in the evaporator coil, and remember it's 75 degrees in the house. So our heat travels from a substance with more heat, which is the air inside the house, to a substance with less heat, which happens to be the refrigerant in the evaporator coil at 40 degrees. And as it does this, this refrigerant starts to change state from liquid to vapor as it moves through the evaporator coil. And remember, this is now absorbing a tremendous amount of heat that it requires to change the state of this refrigerant. As it moves through the evaporator coil, it changes state and continues to do so. When it hits a certain part of the coil, as we go through and change state, at a certain point in the coil, we now have changed state from completely to vapor. So we are now at this point, and it's designed by the manufacturer to have a little bit of evaporator to start to pick up some superheat. So we are 100% vapor at this point right here, and we have now gone out of the cooling mode and the refrigeration mode, and now we're getting into the superheat mode. So now we're 100% vapor at this point, but it is still at 40 degrees. And then as it travels through this part of the coil, it will continue to pick up heat, which is our sensible heat, as it travels through the suction line out to the compressor one more time. And the reason that we want to pick up some additional heat is to make sure we have 100% vapor going back to the compressor, because it will damage this compressor if you have liquid flowing back to it over a period of time. So let's take a look at this. So we have our gauge hooked up here outside. We're taking a look at what's happening right here in the coil, and we discovered it was 40 degrees Fahrenheit. If I'm not careful, I have a face up there before I'm done. And we put our thermometer on the suction line, and we see that it is 50 degrees Fahrenheit. And when you want to measure your superheat, you look at your pressure, you convert it to a temperature, and then you find the difference between the suction line temperature and what you're reading on your gauge as the temperature of the refrigerant in the middle of the coil. And in this case, we have 10 degrees of superheat. All right, so with a properly charged system, we have subcooling, which keeps a solid column of liquid coming up to the metering device. And then we have superheat, which makes sure we have 100% vapor coming back to the compressor. All right. So that is what happens with a properly charged system. Now, what happens if we have an undercharged system? And the one thing I want to make note of before we get into that is this solid column of liquid that is here coming up to the metering device. It's kind of like a traffic jam. The refrigerant's backed up. So, it's backed up right here, and as it meters through, then, half a pound of refrigerant comes through here, pushes on the back, and another half a pound comes out. So it's designed to have this backup of refrigerant here in the condenser coil. So with an undercharged system, let's take a look. So we still have 100% vapor, high pressure, high temperature, superheated vapor coming out of the compressor. And it is going to travel down into the condensing unit. It's going to de-superheat, just like we talked about. Hit that point, it's going to start to, excuse me, it is going to start to change state, and it is going to travel through the condenser, and it's going to turn from vapor to liquid, and it's going to condense its way back down. And what's going to happen is it's going to continue to flow through this condenser, and it's going to flow through this condenser. And because we have less refrigerant, it doesn't back up like it should in the condenser. It continues to travel down here, and then it's going to get to a point where it does back up. So what happens is this refrigerant doesn't spend a lot of time between this point right here and this point right here to pick up subcooling, and it blows through the condenser faster than it should and doesn't back up until it hits right here. So what you'll find, hold on, let's get rid of some of this here. Because it doesn't spend as much time as it should in the condenser and blows its way through there, it doesn't pick up a lot of subcooling. And where your thermometer, instead of reading 105 degrees here, it's going to read 120, or it's going to read 125 degrees, because there is no subcooling happening in the system, because we don't have this backup of refrigerant. And that tends to be a problem, because when you have very little subcooling, then every time this refrigerant, and it's liquid, it's not vapor, it's still liquid, but if it hits a kink, or if it hits a joint, or it has to travel a long way through the liquid line, it starts to drop. If it drops a pound or two of pressure, it's going to start flashing over and boiling over and changing state before it hits the metering device, and that really wreaks havoc on its and air conditioning's capability to cool properly. All right, so what happens is that that refrigerant does not back up and doesn't pick up enough subcooling. And I remember when I first learned subcooling, it was hard for me to get my head wrapped around that superheat and subcooling. Just remember that refrigerant backs up and spends more time in the condenser, and it has more time to get rid of heat, and that's how we get our subcooling. But when we have a low system charge, the refrigerant doesn't spend a lot of time in the condenser, and we have very low subcooling. All right, so we don't have enough refrigerant in the system, first of all, and we'll assume we have a solid column of liquid coming up here to the metering device. Same thing happens as it comes through the metering device. We have 75-25 flash gas going on. We start to change state from liquid to vapor. We're picking up heat, we're picking up heat, we're picking up heat just like it should. And then when with the undercharged system, we don't have enough refrigerant to make it all the way through the coil at changing states. So at a certain point in this evaporator coil, we have now changed state to 100% vapor, and there's no more liquid to change state, and you lose all of this cooling that should be happening in the rest of the evaporator coil. So it's 100% vapor. It's not picking up any heat. It's just picking up superheat, and it's traveling through more of this evaporator coil, picking up more and more and more superheat. And as we get down to the condensing unit, we have we're not going to be measuring 50 degrees anymore. Remember this, we had 40 over here, and we're going to keep the pressures the same for example purposes. It's going to pick up quite a bit of heat. It could be 65, it could be 70 degrees coming out of here, and you're going to have 25 degrees of superheat, and that's your indication of an undercharged system with a fixed metering device. So when you have a fixed metering device and a low system charge, you will have low to no subcooling. You are going to have very, very high superheat. And just remember when the pressure temperature relationship that happens, so when temperature goes up, pressures go up, and vice versa. We're not going to get into that in this example, but I just want you to realize what happens within the system to the refrigerant itself as we go through an undercharged system. So let's take a look at an overcharged system. All right, so we will start again at the compressor, and we have our high pressure, high temperature vapor refrigerant leaving the compressor. It may have superheat, it may not have superheat, but it will begin to de-superheat if there is any, and we'll look at that on the flip side. So as it enters the condensing unit, it's going to change state from vapor to liquid. It's going to get rid of all of that heat. Vapor to liquid, get rid of all of that heat. And what happens is it goes through this condenser just like it should, but instead of beginning to back up here, it backs up earlier on in the condensing unit. So this is now all liquid where it should be changing state. And it backs up this refrigerant. So it spends a longer time in the condenser, and it takes longer to find its way up here to the metering device. And what happens is it picks up more subcooling because this refrigerant is 125 degrees Fahrenheit, and if it's overcharged enough, I mean, you could drop the temperature and add so much superheat that it's almost outdoor air temperature because it's been sitting out here in this condenser with this condenser fan blowing that 95-degree air over it for a longer period of time than it should. And instead of being 105 degrees up here, it might be 95 degrees or 90. Well, it couldn't get below 95, but it could be 95 degrees. And if you do your, I'm sorry, yeah, so that's right. So it's 95 degrees. And then if you measure your subcooling, which is the saturation temperature as measured by your gauge from the physical temperature, if we have 125 and 95, now we have 30 degrees of subcooling. So we pick up tons and tons of subcooling because of the backed up refrigerant in the condenser. Okay, so that makes sense. So we have the refrigerant. The refrigerant is now backed up for a longer period of time in this condenser, and it sheds more heat. So your subcooling increases when the system is overcharged. So we still have that solid column of liquid. We still hit the metering device, 75-25 flash gas, and then we move our way through the evaporator coil, changing state, changing state, changing state, changing state, continues to change state. But because there's too much refrigerant in the system, instead of being 100% vapor at this point, it's still changing state. There's still liquid in the system, and it works its way down here. It's changing state, changing state, changing state. It's still liquid and vapor because it's overcharged. And we bring liquid back to the compressor, and it might only be 90%. It might only be 10% liquid and 90% vapor, but we still have liquid nonetheless. And because we're still changing state as it exits the evaporator coil, instead of measuring 50 degrees Fahrenheit here, it's going to be 40 degrees, because remember we looked at the 69 PSIG, and that is equivalent to 40 degrees Fahrenheit, because that's what's happening right here, where it should be changing state and picking up lots of heat, and it's still changing state as it comes out here. So the temperature at this point and at this point are the same. So you have, with an overcharged system, you have low to no subcooling, and you have very high superheat in a fixed metering device system. All right, I hope that I didn't lose you on that, because I can't see your faces to see if you have that confused look on your face, like I'm talking in a different language and way too fast. But let's take a look and see if you have any questions. Let's just move on here. And we can always go back if there are questions. Let me take a look and see what you got. Okay, any questions about the refrigeration cycles, the effects that it has on the fixed metering device with an overcharge and undercharge? And this video will be available to watch as well. And thank goodness that all of the systems worked, at least on my end. Well, I'll review the video and find that out on your end. All right, last time for question, guys. All right, so you can email me, reach me through Google+, call me on the phone. If I can do anything for you and help you, please let me know. And Andy, if you're still with me, I will be more than happy to answer your question for you. Okay, Andy, if you're still with me, go ahead and type in there your question, and I'll see if we can figure out your soda machine. What kind of metering device does it have? Or what kind of metering devices do they have? Well, all right. Well, I guess we lost Andy on that one. All right, gents, thank you very much. In the next couple of weeks, keep your eye open. We're going to be doing TXVs and how they operate. Then we'll take a look at how the refrigeration cycle and overcharge and undercharge affects the TXV system.